Hey guys, welcome back to Professor Z Academy. In this episode, we're going to be covering some of the applications of integrals regarding volume and area. And we're also going to be going over AP FRQs at the end of the video. So if at any point during the video you feel like you've understood the concept and you want to see it applied to real-world problems, go to the end of the video, and there I'll be going over AP FRQs. Before we start talking about volume, though, we need to talk about area. Specifically, the area between two graphs or two curves. So how do we do this? Well, let me just take two graphs here. So let's say I have the curve y is equal to square root x, right? And then I have a second curve. And please excuse the bad drawing, but this is y equals x. And then we're asked to find the area of this region here, which I'll call A, of the intersection between these two curves. So if you don't understand what I mean this shaded area. Now, how might we do that? So let's recall that integrals are essentially the area underneath the graph. So if I draw out these two graphs, this is y equals root x, and this is y equals x, we find that the integral of root x dx is this shaded area underneath. While the integral of x dx with respect to x is going to be this shaded area underneath. What we can then notice is that the area of A is going to be this larger area subtracted from this smaller area. So if we take this big area up here, and from that we subtract the smaller area, we should get the shaded region. And we can do this because, in this case, from these points, root x is higher than x. So the area underneath that graph is going to be larger. Now the question becomes, when we integrate, what are our bounds? Well, we need to notice that these two graphs, they intersect at 0, 0, and they intersect again at 1, 1. So our bounds are going to be from 0 to 1, x equals 0 to x equals 1. Let me just draw a dotted line. So let's take these integrals, right? So we need to take the area of the larger, higher curve, and which will be the bigger area, the entire area. So it's going to be the integral from 0 to 1 of root x dx. And from that, we want to subtract this lower area, this smaller area, from 0 to 1 of x dx. And there you have it. That's the area of A. Of course, if we evaluate this integral, we'll get, I'll move this over here, x to the 3/2 times 2/3 bounded from 0 to 1 minus x squared by 2 from 0 to 1. Which is equal to 2/3 minus 1/2, which is ultimately equal to 1/6. And that is the area of A. So that's a general concept, is that when we have these two curves, we need to find the higher graph, or the outer graph, the graph that has a larger area underneath it, which in this case is the root x. And from that, we need to subtract the graph that has a lower area, which is x, or the graph that is underneath the higher graph. And by subtracting the lower area from this higher area, we'll eventually get the desired shape, right? The desired area between the curves. Let's look at another example. In this case, my two curves are going to be y equals x and y equals x plus sine x. And I want to find the area between the curves from the domain 0 to 2 pi. How would I go along doing that? So let me draw out the situation. This is y equals x. And y equals x plus sine x should look something like this. Extend this graph. Where this is going to be 2 pi. 2 pi, 2 pi. Now immediately notice that this point right here, which we can calculate to be pi, the y equals x graph overtakes the y equals x plus sine x graph. And what ends up happening is that the y equals x graph has the larger area in this section. The area underneath the y equals x graph is larger than the area underneath the y equals x plus sine x graph from pi to 2 pi. While in here, it's the y equals x plus sine x that has a higher area underneath it than the y equals x graph from the domain 0 to pi. How do we approach this kind of problem? Well, there's two kinds of approaches. The first one is the most intuitive, which is that we can split up these areas, which I'll call A and B, and we can find each one independently and then add them together at the end. So how do we solve for A? Well, in this case, the y equals x plus sine x has the larger area underneath it. So we take this bigger area and subtract the smaller area, and we're going to get the area of A. So that's going to be the integral from 0 to pi of x plus sine x dx minus the integral from 0 to pi of x dx. Okay. And then B, in this case, it's the y equals x graph that has the higher area underneath it. So we're going to take this whole area and subtract this bit in order to get the desired area of B. That means the integral from pi to 2 pi of x minus the integral of pi to 2 pi of x plus sine x. So what we can do here is that because both of these integrals have the same bounds, we can combine them. And we'll get x plus sine x minus x dx. But the thing is, these x's, they cancel out. So we're just left with sine x dx. And here, we're left with the same thing, because these x's will cancel out. And we'll get pi to 2 pi of sine x dx. So let me just erase this and then rewrite it so we have some more room. But, right. So we know that A is equal to the integral from 0 to pi of sine x dx This is, of course, equal to negative cosine x bounded from 0 to pi, which is going to be negative 1 minus -1, giving us 2. Now for b, pi to 2 pi of sine x dx is again going to be negative cosine x from pi to 2 pi. It's going to give us -1 minus, sorry, I made a slight error. This should be negative because it'll be x minus integral x plus sine x. So actually this will end up being integral of negative sine x. Forgive the error. Hopefully you can forgive me. But that means it's just cosine x from 2 pi to pi, which is going to be 1 minus -1 is again 2. So, wait a minute. A and B have the exact same area. And that leads us to the second approach to solving this problem. In this case, you can actually notice that A and B are the same area. And that's because sine x is a periodic function. So the area underneath the A is going to be the same as the area under the B. But it's just an interesting tidbit. If you notice any kind of symmetry in a problem, try to take advantage of it. And instead of having to calculate the integral twice, you can just multiply the area by 2. So let's just get rid of this. And now the last thing. If you have a calculator during a test, which you will have during the AP Calculus BC calculator section, instead of doing all this, you can simply enter into your calculator 0 to 2 pi of the absolute value of x minus x plus sine x. And the way we got this is it's the absolute value of the integral from 0 to 2 pi of x dx minus, sorry, so the way we got this is that, just give me a second. What you notice here is that by using this absolute value, we don't actually have to care about the higher and lower. Which one is higher, which one's lower? We don't have to keep track of that. And the reason for that is because higher minus lower, so the area under the higher graph minus the area under the lower graph. So let's say this is the area we're trying to find. It's just the negative times lower minus higher. And what that means is that the magnitude of A, of these two, higher, lower, absolute value of these two, is always just going to be A. So if we have a calculator, we don't actually have to care which one is higher, which one is lower. As long as we have an absolute value in there, the calculator will just take care of this whole thing. But of course, if you don't have a calculator, you need to check which graph has a higher area underneath it and when. Otherwise, what's going to happen is if you just directly evaluated 0 to 2 pi, so let's get rid of these absolute value. If we just directly evaluated the sum, we'd get 0. Because A would have with some area of 2, and B, using this equation, would have an area of -2, which you can't have a negative area. But the integral would give you 0, and you'd be left to wonder, how can this be 0? Okay. So now that we've talked about area between the curves, we can talk about volume. The most basic type of volume is a volume of a cross-section. And what this means is that in the AP test, they're going to give you an area, and they'll tell you that a 3D shape is made by using a cross-section, and they'll ask you for the area, for the volume of this shape. Let's take a look at an example. So most of the applications of integrals that I'll be going over this video are geometric. So you really need to draw the situation out, and you can better visualize the scenario and use geometry to solve these problems. A lot of the question is actually setting up the integral rather than it is to evaluating the integral. So as we're going along these steps, we're going to talk about what everything means. So let's say we're given the question, find the volume. Let me change my color. Okay, okay. Let's say we're told to find the volume of a solid whose base is bounded by x squared plus y squared equals 9. And the area is a cross-section taken perpendicular to the x-axis with an isosceles right triangle with legs meeting at right angles on the base. What does this mean? Well, what does this mean? So let me draw out this graph. You see here, x squared plus y squared equals 9 is just a circle. And now pretend for a second that this is on a sheet of paper. What I'm going to do is I'm going to move this paper to an angle like so. So you're seeing above this piece of paper, and this is our circle. What they're saying is that if you take this cross-section of the circle, you're drawing an isosceles right triangle above the circle. An isosceles right triangle meaning that this height and this base are the same. And you just keep doing that. You keep doing that. And you'll get some sort of solid, which will look something like this. It's a little hard to draw a solid on a 2D graph, but it'll look something like this. Okay, how do we solve for that? Okay, so what does this mean? And how can we solve this kind of question? First of all, we need to find the cross-section of this graph. And then we need to use that to find the volume of the shape that we're creating. So think about it like this, right? Once we identify this cross-section, an isosceles right triangle, and let's say this has a length of x, or sorry, r, the height is going to be the exact same. Height's going to be the exact same. And if the height is the same, that means that the area of this triangle is going to be half r squared. Right, because the area of a triangle is base times height times 1/2. And what we're doing is we're taking all these little cross sections, right? And we're extending them by a very marginal amount. We're creating the rectangle. So recall the Riemann sum is adding up a bunch of rectangles. In this case, we're adding up a bunch of very thin strips of these triangles, and we're creating the volume. How thin? Well, we'll multiply this area times a width of dx, where in this case dx means that very, very small amount, this very small change in x, and that's the width that we're multiplying. So let's take a pause here and see if you understand. What we're doing is we're taking this small cross section, we're extending it upwards in the shape of this triangle because that's what's given, and we extend it a little bit with dx to take a width. And once we add all of those little slips of triangles up, we'll end up with our solid. And how do we add things up? We take the integral, of course. So, and of course, we want to take bound our integral. So the circle is from -3 to 3. So our integral is going to be from -3 to 3. Now the question is, what is R? Meaning, what is this cross section? Well, for that, we're going to have to do a little bit of geometry to figure it out. So what is the cross section that we're trying to find? Well, as we mentioned, I'm going to have to do a little bit of geometry. So in a circle, in this case, this height above is equal to this height below because it's symmetric, it's a circle. So at any point, x, y, how do we find this y? How do we find this height above this midline? We want this height. Well, we take our equation, and we rearrange it. So we'll get y squared is equal to 9 minus x squared, which gives us y is equal to square root 9 minus x squared. So what that means is this height right here from y equals 0 to this point is square root 9 minus x squared. But that's not the entire height of the cross section. We also need down here. And this length is also square root 9 minus x squared. And you might be saying, how do we get this, other than the fact that it's just symmetric, is that this is actually a plus or minus square root. So there's two answers for it because it's a squared. So because it's a plus or minus, it'll go plus root 9 by x squared and minus root 9 minus x squared. Okay. So now we know that the length of the cross section, meaning if I take a little cut across the circle, the length of that cut is going to be 2 times square root 9 minus x squared, where x is the point I'm taking the cut at. Great. So now we have everything, and we can just put it into our integral and evaluate. Let me just erase all my diagrams. So if we input this into our value of r, what we're going to get is we'll get the integral from -3 to 3 of 1/2 times 4, so just 2, times 9 minus x squared. And that's because it's r squared, and our r is 2 root 9 minus x squared. So if we square that, we'll get 4 times 9 minus x squared. And this is dx. So this, of course, will give us 2 times the integral from -3 to 3 of 9 minus x squared dx, which of course gives us 2 times the value 9x minus x cubed by 3 from -3 to 3. And from there, we'll get something like, so the first one will be 27 minus 9, 18, minus -27 minus 9. It's going to be minus 36. So if we evaluate this, what we're going to get is 108. as our volume. So as you see, the integration was just an extremely small aspect of what we're actually doing. And I'm going to go over again what we did just to clarify what this means by cross-section volume. So what we did is we took the graph, we took a cross-section of that graph, and then we extended upwards in the triangle, and we multiplied that area by a very small width of dx. And what we're going to get is an extremely thin rectangle right here. And with that extremely thin rectangle, we added all of those extremely thin rectangles up. Sorry, did I say rectangle? I meant triangular solid. We took all of those extremely small triangular solids, we add slips, and we added them up, and we get the total shape. And now also notice that this height of the triangle wasn't constant. It was changing across our shape. And we had to account for that in our function. Now we're going to talk about a different kind of volume. So recall that for the area between two graphs, I said that the integral is, if I take a random shape, it's the area under the curve. That's not exactly true. Well, it is, but more specifically, what we did is we split up the graph into very, very tiny rectangles. Riemann integrals, if you recall your Riemann sum. Riemann rectangles. And we found that the height would be f of x, the width would be d of x, or dx, a very thin width, and we summed all of them up, and we call that our integral, which would give us the area. So now, let's say I have some sort of curve like this, and they asked us to find the volume of that curve around an axis, meaning that it should look something like this sort of weird shape. How do we go about doing that? So what we can do is, instead of adding up little rectangles, if we take up these little rectangles and we rotate them around the axis, what we will instead get are these little thin discs. And excuse the poor drawing. So what we can do is, to find the volume, we can add up all these thin little discs and eventually get the whole shape. So we treat the solid like the sum of these discs, or cylinders. Let's take an example. All right. Let's say that I have the graph. Let's say I have y is equal to x squared plus 2, bounded from x equals 0 and x equals 2. And we want to find the volume of this rotated around the x-axis. So let me just draw this out. So x squared plus 2 is going to look something like this. And it's bounded by, from x equals 2, 0, which is here, and x equals 2 here. So this area right here. And we want to rotate that around the x-axis. So you'll get something that looks like this. This is our solid. So, as I mentioned, we're going to add up all these small little cylinders and get the total volume. Now, what is the volume of the cylinder again? Well, it's going to be pi times your radius squared times your height. So in this case, for an extremely small cylinder, pi is the same, but the r is going to be how far away we are from the x-axis. So luckily, we have a function for that. It's called y. So in this case, it's going to be pi y squared. And our height is going to be, if we draw out this little rectangle, I said that we're going to, or this cylinder, I said that we're going to take very, very thin disks and add them up. So as you probably can guess by now, the height of this is going to be dx. And we want to integrate this from 0 to 2. So, but we have y here. How can we deal with that? Well, great. We're actually given y by the graph, x squared plus 2. So let's take pi out of the integral because it's a constant. And our integral becomes from 0 to 2, x squared plus 2 whole squared dx. Now again, what we're doing here is we're taking the volume of this rotated graph by adding up all these little cylinders or disks. And this volume of a small disk is going to be pi r squared h, where r is how far away it is from the axis that we're rotating around. In this case, we're rotating around the x-axis. So if the radius is going to be y, it's going to be f of x, or y, and our h is going to be dx. And that's how we get the integral. Now, of course, we could evaluate the integral. But for the sake of time, we're going to leave that. Because as I've emphasized time and time again, it's not about the integral. It's about what the integral means and how you're getting to that point. So when you get a problem, don't try to just memorize the formula and then put it in. Try to understand exactly what we're doing here, right? If we have this equation, integral of pi r squared h, you need to understand what actually we're doing, which is taking these small little disks, adding them up. And that's how you're able to find r, and that's how you're able to find h. Okay. Let's take another look at another example. In this case, we're given asked to find the volume of the solid of the shape y equals x cubed, bounded by x equals 0 and y equals 8. About the y-axis. So in this case, let's talk about this. So the first thing to do is we want to graph our function y equals x cubed. And what that's going to look like is it's going to look something like this. And we're saying that we're bounded by x equals 0 and y equals 8. So y equals 8. Sorry, x equals 0 is here. And y equals 8. So this area, and we want to rotate this around the y-axis. So we'll get something that looks like this. This weird shape. Now, again, we want to add up these small little cylinders. So let's find the volume of one of these small cylinders. So we have pi, and let's talk about r. So r is going to be how far away we are from the y-axis. Well, that's just x. So we're going to do pi x squared. And the height of this small cylinder, h, if you see here, it's going to be a very small change in y. So dy. And we want to integrate this. Wait a minute, you might be saying we have x squared and we have dy. You can't integrate that. Exactly, you can't. What we need to do is we need to take our original function and we need to use that to find x. So in this case, x squared is going to be y to the 3/2. Sorry, y to the 2/3. And of course, we need to add up these little cylinders from this point up till here. So that's going to be from y equals 0 to y equals 8. So the bounds of our integral are going to be the integral from 0 to 8 pi y to the 2/3 dy. And again, I'm not going to evaluate this integral because it's simple power rule. And the most important part is understanding that how we got to that integral in the first place. We add up the little cylinders, and we need to find the volume of each of these little cylinders that we add up, these little disks. Okay, seems easy, right? Let's try another problem. How about y is equal to 2x squared Sorry, that's the wrong question. Let's take a look at the question of let's say we have two graphs. Y equals root x. Again, this is the same from the normal, from the first one we talked about. And y equals x. And we want to find the shape of the volume that is or the volume of the shape that is created when we rotate this around the x-axis. Hold on, you might be saying. What the heck? How are we going to find this volume, right? If we try to apply our simple formula of applying these disks together, it's almost impossible to find the volume of these little disks to sum up this area. Well, what do we do in the cross-section area video? Or in the first part of the lecture, we took the area under the y equals x squared x graph, and from that we subtracted the area under the y equals x graph. In a similar way, the volume for this little area is actually going to be the volume of this bigger y equals root x spun around the x-axis. And from that, we subtract the volume of the smaller y equals root x. In exchange, after the calculations, we'll be left with the volume of this shape rotated around the x-axis. And what this is called the washer method. It's called a washer because if you know nuts and bolts, a washer is a ring with a hollow center. And in this case, what we're doing is we're adding up the bigger cylinder, the outer cylinder, and we're subtracting away the area of our inner cylinder, and we're left with just this ring. And that's how we add them up. So in this case, that means we'll have pi r squared, big R squared h, where big R is the radius of the bigger cylinder. And from that, we subtract pi little r squared h, where this is little r. And that's going to be the area of our little ring. And we add up those rings, and we'll get the volume of this shape. So in this case, the bigger r, let's set up the values, right? The bigger r is going to be how far away we are from this x-axis. Well, again, it's y. So it's going to be square root x squared. And our height is going to be the little change in x. Similarly, this will be pi x squared dx. So essentially, the volume of our ring is going to be pi x minus pi x squared, because we can factor out this dx. And then we add all those little rings up, and as we discussed in the first problem, the bounds are going to be from 0 to 1. And that's it. And that's, so again, we need to understand how we got this integral. This right here is our outer radius. It's the bigger ring that you can see here. And in here, this is a smaller ring, the area of the smaller disk. If we subtract the area of this bigger disk from the smaller disk, we're left with the area of a ring, which we multiply by the width dx, getting a very small washer. So if I rotated this shape around the x-axis, and we used our rings method, you'd be left with something like this. You add all your washers together, and you get the volume of this, rotated around the x-axis. Okay, all of this seems great, right? That means we can try another question. Great. So y equals 2x squared minus x cubed bounded by y equals 0. And we want to resolve this around the y-axis. Great. Such a nice, easy question now that we know our disk method. So this graph is going to look something like this. Bounded by y equals 0. So this area revolved around the y equals x. Wait a minute. Uh-oh. There seems to be a problem. Even with our disks, right? There's a gap here. We can't just take our normal cylinders and add them up. And in this case, this is even weirder. This outer, if we kind of think of this as like a washer, right? This outer function and this inner function are the same function. So how are we going to subtract the same function from the same function? This is extremely confusing, right? That's where the cylindrical shell method comes in. And it's another technique that can be used in situations like this. Instead of treating the solid like a sum of disks like this, we can instead take a hollow cylinder, which we'll call a shell, a cylindrical shell, and then inside we can put another hollow cylinder, and another one, and another one. And if I keep adding this, I'll eventually get this weird volume, 3D volume. So my diagram might not have explained it fully, but think about a Russian doll, a Russian nesting doll. That volume is made up of a bunch of big dolls containing smaller dolls, containing smaller dolls, containing smaller dolls, containing smaller dolls, etc. And similarly, we can take these hollow shapes, add them up, and we'll end up with the full volume. So in this example, what we need to do is we need to take a hollow cylinder here and add it up with this hollow cylinder here and keep adding. So we need to find the volume of these hollow cylinders. So how exactly do we do that? Well, recall that in a cylinder, the surface area, or the perimeter of the cylinder, or the circle on the cylinder, is going to be 2 pi r times h. Is going to be this outside area. Now, if we extend that and multiply by small width, small thickness, which in this case I'll call dx, even though it's not always dx, we'll end up with the small hollow cylinder. So in this case, what we're doing is we're building a hollow cylinder around the shape. A better way to think about it, if you're not fully understanding this hollow cylinder thing, is if I split this shape up into a bunch of little rectangles, this way, and I rotate each of those around, I'll end up with the cylinder. And if we add up all these rectangles and spin them around, we'll get the area. So the volume, I mean. So the volume of each of these rectangles spun around is going to be 2 pi r, where r is the distance away from the axis, times their height, times their thickness. Again. Okay, so for this shape, what does all this mean, right? 2 pi is going to stay 2 pi. But what is r? R, how far away you are from this y-axis. Well, great, that's just x. Right, so we can just slap on an x here. And then our height is going to be our y, which is given to us as 2x squared minus x cubed. I should have finished this. And then our thickness is the thickness of these little rectangles is going to be dx. Now the question is, what are our bounds? Well, it's going to be wherever this shape intersects y equals 0, and then wherever this shape intersects y equals 0. So if you set these two equal to each other and you find the intersection points, you'll get that the bounds are 0 to 2. And this is our integral. We've summed up all these hollow cylinders, and we'll get the total volume. Great. Now that we've gone over all the main concepts that College Board asks you about on the AP test in regards to volume, we can try some problems out. And these are taken from real AP FRQs. This one is from 2022. Pretty recent. In the figure 1 and 2 shown above, illustrate regions in the first quadrant associated with graphs of y equals 1 over x and y equals 1 over x squared. In figure 1, let R be the region bounded by the graph of y equals 1 and by x, the x-axis, and the vertical lines x equals 1 and x equals 5. In figure 2, let W be the unbounded region between the graphs of y equals 1 by x squared and the x-axis that lies to the right of the vertical line x equals 3. Question A, find the area of the region R. Well, this is pretty easy. It's just the area under the graph. So you take our integral 1 to 5 of our function 1 by x dx. Great. This is just going to be equal to ln x from 1 to 5, which is just equal to ln 5. Because ln 5 minus ln 1 is 0. So ln 5. Question B, region R is the base of the solid. For the solid, at each x, the cross-section perpendicular to the x-axis, meaning cross-section like this, is a rectangle with area given by x e to the x by 5. Find the volume of the solid. Well, okay. The area of the rectangle is just going to be x times e to the x by 5, which means that all we need to do is add up the area of these rectangles and multiply them by a small little width, which we'll call dx. So since the area of the rectangle is already given to us, all we need to do is multiply it by the thickness to get that volume. So again, we bound our integral from 1 to 5, and the area is given as x e to the x by 5. With respect to x. So in order to evaluate this integral, we'll have to use integration by parts. So let's say that u is equal to x, dv is equal to e to the x by 5, which means that v is going to be the integral of that. So 5 e to the x by 5, and du will just be dx. So that means this is 5x e to the x by 5, bounded from 1 to 5, minus the integral from 1 to 5 of v du. So 5 e to the x by 5 dx. I assume you know how to do the rest. And then C, find the volume of the solid generated when this unbounded region W is revolved around the x-axis. This unbounded region. So what does that mean, right? We want to rotate it around the x-axis, which means we can use our disk technique to form these little cylinders. So the area of each cylinder, or the volume of each cylinder, a little disk, is going to be pi r squared h. So in this case, r is going to be y. And our h is going to be our thickness, which is dx. So this is just, and y is given as 1 by x to the 4th, or x squared. So 1 by x squared dx equals pi by x to the 4th dx. And what are our bounds? Well, our bounds are 3 to unbounded, which means infinity. So we have to use our improper integral here. So limit as b approaches infinity of the integral from 3 to b pi over x to the 4th dx. Let me just make some room real quick. So we said the integral from 3 to b, lim as b approaches infinity, pi over x to the 4th dx. So this is going to be equal to pi over negative 3 x to the 3rd from bounded from 3 to b, and as b approaches infinity, which is equal to negative pi over 3b cubed minus pi over 81 and limit as b approaches infinity. So because b is approaching infinity, we can actually evaluate this. B is in the denominator here, so as it's approaching infinity, this actually goes to 0. And eventually all we're left with is pi over 81, which is our answer. Okay, find the area of R. So let R be a shaded area bounded by y equals ln x and the line y equals x minus 2. Find the area of R. Find the volume of solid generated when R is rotated about the line y equals negative 3. Right, but do not evaluate an integral expression used to find the volume of the solid generated when R is rotated around the y-axis. So this is pretty simple. We see up here that ln x is our upper function and x minus 2 is our lower function. And the bounds of our integrals are going to be the intersection points of these two. So where do they intersect, right? Ln x equals x minus 2. So the thing with this question is it's actually calculator based. I forgot to mention that. So in order to find the intersection points, what we need to do is go into our calculator, graph these two functions, and find the intersection points between them. So if I get my calculator out, and then I graph it, calculate the intersection, we'll find that the lower bound is going to be 0.159, and our upper bound is going to be 3.146. Okay, and our higher function is going to be ln x. And we want to subtract our lower function, x minus 2 dx. So I can just plug this into our calculator from 0.159 to 146 ln x minus 2. We'll get 1.9. And if you don't know how to do an integral on the calculator, it's just going to be second math, and then you just go to math, not second, go to math and click the 9th option, which is fn int. Anyway, B, find the volume of the solid generated when r is rotated around the horizontal line y equals -3, which is down here. So how do we do this? We have a gap here. What we can do is we can use our washers method. So we need to find the area of each washer. Integral. So the area of each washer is going to be the outer disk subtracted from the inner disk. So it's going to be pi ln x squared minus pi x minus 2 squared. Oh, and here's an extremely important thing to notice. When our r is actually not going to be ln x here, because it needs to be the distance away from our axis. And ln x is the distance away from x equals 0. So what can we do about that? We need to shift our axis so that we're actually finding this distance. So what that means is we actually need to add 3 to our radii. Ln x plus 3 squared minus pi, so x minus 2 plus 3 is just going to be x plus 1 squared dx. So you might be saying why plus 3, not why minus 3? It's because our new axis is down, so it's further away from this. So if we take this point up here, for example, this is going to be ln x, and it'll be 3. So the distance from this point to the bottom is ln x plus 3. And you might be saying, what about over here when these values are negative? Well, if ln x is negative, that means this distance is actually going to be negative ln x, because this value over here is negative. So we need to do 3 minus the distance, which is going to be minus ln x. And we'll just end up getting 3 plus ln x. Or in other words, because this distance is negative, this ln x is negative at this point, if we add 3 plus a negative value, we're going to get something less than 3, which makes sense because these functions are closer to the axis here. So this is our integral, and our bounds are the same. And it's going to be our 0.159 to our 3.146. which we can solve with the aid of a calculator, but it's unnecessary. Write but do not evaluate an integral expression that can be used to find the volume of the solid generated when r is rotated around the y-axis. Okay, y-axis. Let's once again go through our list of techniques. Can we use disk? No, because it's not directly touching the y-axis. Can we use hollow cylinder or cylindrical shells? Well, the cross-section, the volume of the hollow cylinder is going to be extremely difficult to take here, actually. So instead, what we need to do is we need to use our washer's method, specifically around the y-axis. So the area of this outer disk, well, what we need to do is we need to tilt it. So let's redraw our graph. Let's do this is x. This is y. It'll look something like this. So we need to take our disk area. So our outer disk is going to be pi r squared, big R squared, times our thickness, or h. And in this case, our thickness is going to be dy, and r is x, so pi x squared dy. And it's the same thing with the other one. So we need to rearrange the function to get x. So for y equals ln x, that's the same thing as saying x is equal to e to the y. And for y equals x minus 2, that's the same thing as x is equal to y plus 2. So we need to take the outer disk from the intersection points, which again can be found using a calculator. So we need to this time find the y bounds. So the upper is going to be 1.14, while the lower is going to be negative 1.84. So just sum up all the cylinders together. So the first one is pi e to the y squared. Or sorry. What we notice here is that the one that's actually further away from this x-axis is going to be this line. It's the outer disk. So it's actually going to be y plus 2 whole squared dy minus these. Pi e to the y squared dy. Okay. And it says do not evaluate, so we can just leave it like this. Finally, our last question. I lied. Second to last question. A company designed spinning toys using a family of functions of y equals cx root 4 minus x squared. Receives a positive constant. The figure above shows the region in the first quadrant bounded by the x-axis and the graph of y equals cx squared root 4 minus x squared for some c. Each toy is in the shape of the solid generated when such a region is rotated around the x-axis. Find the area of the region bounded by the x-axis and the graph of y equals cx root 4 minus x squared for c equals 6. Okay, well that's pretty simple. We need to find when this is 0, because it's bounded by the x-axis. And that's pretty obviously 0 and 2. So our bounds are 0 to 2. C is 6, so it's going to be 6x root 4 minus x squared dx. And in this case, to evaluate this integral, you would use u substitution, where u is equal to 4 minus x squared. Now, for the sake of time, we're not going to go over that. B. It is now known that for y equals cx, dy by dx is equal to this. For a particular radius, the radius of the largest cross-sectional area slice is 1.2 inches. So what is the value of c? So the largest cross-sectional slice is basically saying up here, when y is at its max. So recall that something that its maximum when the derivative is equal to 0. So if we set this to 0, what we'll find is that what we actually want is we want 4 minus 2x squared to be 0, because everything else is, the c we can get rid of because it's a constant, and the denominator is the denominator. We can multiply by it on both sides, and we'll just end up with this. Therefore, it reaches its maximum when x equals root 2. So now we want to find c. We're given that the radius is 1.2, so at this maximum point. So that means 1.2 is equal to c times square root 2 times root 4 minus x squared, so which is another square root 2. Giving us a value of c is equal to 0.6, because root 2 times root 2 is 2, just left with 1.2. For another spinning toy, the volume is 2 pi cubic inches. What is the value of c for this spinning toy? Okay, so what we need to do is we need to find the volume and set it equal to 2 pi. So I'm going to make this a little smaller so we have more room. And erase this. But we need to find the volume. So the volume is, we can actually use the disk method. It's a sum all these little disks. So the volume of one disk is going to be pi times r, which is just cx root 4 minus x squared, squared times our height, which is going to be dx. And we integrate that from 0 to 2. And the general gist is that you set this to 2 pi, and you'll solve for c. But unfortunately, that's all the time I have for today. So thank you so much for watching. Please let me know what you think about the video, if it was helpful, if it wasn't helpful. And if you have any questions, please leave them in the comments below, and I'll try my best to answer them. Thank you, and good luck with whatever you're doing.